Can you imagine a world where the secrets of heat and light are still mysteries? In 1911, Wilhelm Wien was awarded the Nobel Prize in Physics for his discoveries regarding the laws governing the radiation of heat. His most notable contribution, Wien's displacement law, reveals the relationship between the temperature of a body and the wavelength at which it emits radiation most strongly. But how does this apply to real life? Consider the simple act of heating a metal object. Initially, it glows red, but as it gets hotter, the color shifts to white. Wien's law explains this phenomenon, providing insights into the temperature of stars simply by analyzing the color of light they emit. What might this law mean for understanding the universe's most massive and hot objects? Imagine the perilous journey of sailors navigating the dark seas, their safety depending on the guiding light from lighthouses. In 1912, Gustav Dalén was awarded the Nobel Prize for his invention of automatic regulators, used in conjunction with gas accumulators for illuminating lighthouses and buoys. His invention, the sun valve, controlled the light so that it only operated from sunset to sunrise, conserving fuel and extending maintenance intervals. But what makes Dalén's story even more remarkable? After an accident left him blind, he continued his work, demonstrating extraordinary perseverance. Think about the lighthouses dotting the world's coastlines. How many ships found their way to safety, guided by the light that Dalén's invention helped shine? Now, let's venture into the cold, a realm so frigid that materials behave in unimaginable ways. In 1913, Heike Kamerlingh Onnes received the Nobel Prize for his investigations into the properties of matter at low temperatures, which led to the production of liquid helium. His most revolutionary discovery was superconductivity observed in mercury at a temperature close to absolute zero. Why is superconductivity a monumental discovery? Imagine a world where electricity can flow indefinitely without any resistance, potentially revolutionizing how we use and transmit power. Onnes's work not only provided a deeper understanding of quantum mechanics, but also laid the groundwork for future technologies, from maglev trains to MRI machines. What future innovations might arise from this chilly frontier of science? In 1914, the Nobel Prize in Physics was awarded to Max von Laue for his discovery of the diffraction of X-rays by crystals. This discovery not only proved the wave nature of X-rays, but also opened up a new field in physics and chemistry, X-ray crystallography. But what does this mean? Imagine a world where the atomic structure of materials remained a mystery. Von Laue's work provided a microscope that could peer into the atomic world, revealing the arrangement of atoms and crystals. How might this breakthrough have transformed our understanding of materials and aided in the development of new drugs and materials? The year 1915 saw the father and son duo of William Henry Bragg and William Lawrence Bragg jointly awarded the Nobel Prize for their services in the analysis of crystal structure by means of X-rays. Their work built directly on von Laue's discovery, developing the law of Bragg diffraction, which became fundamental for the entire field of X-ray crystallography. But what's the significance of this? Imagine a world where the structure of DNA, the blueprint of life, remained undiscovered. The Bragg's method was pivotal in determining the structure of many complex substances, including vitamins, hormones, and most famously, DNA. How might their work have revolutionized fields from medicine to materials science? Interestingly, in 1916, the Nobel Prize in Physics was not awarded. The First World War was raging, and such tumultuous times impacted not just global politics and societies, but also the scientific community and its recognitions. The absence of a laureate this year is a poignant reminder of how science, while a beacon of progress and understanding, does not exist in isolation, but is part of the broader human experience, susceptible to the ebb and flow of historical events. In 1917, Charles Glover Barkla was awarded the Nobel Prize in Physics for his discovery of the characteristic X-rays of elements. Imagine a world just beginning to understand the deeper, hidden nature of atoms. Barkla's work revealed that each element has its own characteristic X-ray spectrum, akin to a unique fingerprint. How might this revelation have changed the way scientists identify and understand elements? His discoveries not only furthered the field of spectroscopy, but also had practical applications in both chemical analysis and medical diagnostics, allowing doctors to see inside the human body like never before. The year 1918 marked the recognition of Max Planck, who was awarded the Nobel Prize for his discovery of energy quanta. Planck's work is foundational to quantum theory. He introduced the concept of quantized energy levels, which led to a profound shift in our understanding of atomic and subatomic processes. But what does this mean in simple terms? Imagine the universe as a grand stage of energy, where instead of flowing smoothly, energy exists in discrete packets, or quanta. Planck's discovery challenged classical physics and laid the groundwork for the quantum revolution that would follow. How might his revolutionary idea have paved the way for the technologies we rely on today, from computers to communication systems? In 1919, Johannes Stark was awarded the Nobel Prize for his discovery of the Doppler effect in canal rays and the splitting of spectral lines in electric fields, known as the Stark effect. This discovery is crucial in the field of spectroscopy. But what's the broader impact? Imagine the ability to understand not just the composition of atoms, but also their behavior in various environments. The Stark effect provides insights into the structure of atoms and molecules, and how they interact with electric fields. How might this knowledge have advanced the fields of atomic physics, quantum mechanics, and even helped in understanding chemical reactions and designing new materials? In 1920, the Nobel Prize in Physics was awarded to Charles-Édouard Guillaume for his work on the anomalies in nickel-steel alloys, leading to the discovery of the alloy Invar. But what does this mean, and why is it significant? Guillaume's discovery of Invar, an alloy with a remarkably low coefficient of thermal expansion, revolutionized precision measurements and instrument manufacturing. Invar's unique property of hardly expanding or contracting with temperature changes made it an ideal material for precision instruments like clocks, scientific instruments, and even parts of machinery where stability is crucial. Imagine a world where every slight temperature fluctuation could throw off sensitive measurements. How might Guillaume's work have transformed not only scientific research but also various industries relying on precision engineering? In 1921, the world of physics was forever changed as Albert Einstein received the Nobel Prize for his revolutionary work on the photoelectric effect, reshaping our understanding of light and laying the groundwork for quantum theory. This wasn't just any discovery. It was a radical departure from the classical view that light was solely a wave phenomenon. Einstein proposed that light could also be described as discrete packets of energy, known as photons, fundamentally altering our grasp of the universe's building blocks. But what does this mean in practical terms? Imagine a world without the technology we often take for granted. Solar panels, which convert sunlight into electricity, rely on the photoelectric effect to harness energy. Digital cameras capture our most cherished moments by using the same principles to convert light into electronic signals. Even our understanding of stars and distant galaxies depends on the insights provided by this Nobel-winning idea. Einstein's photoelectric effect isn't just a theory tucked away in textbooks. It's a principle that powers innovation and technology, driving us towards a future full of potential. As we delve deeper into the atomic world, his legacy continues to inspire new generations, proving that our quest for knowledge is as boundless as the universe itself. So, why didn't Einstein receive the Nobel Prize for these monumental theories? The Nobel Committee often favored discoveries that could be empirically verified and had practical applications. In the early 20th century, relativity was still considered controversial and far from experimentally proven to the standards of the Nobel Committee. The photoelectric effect, on the other hand, had clear, observable implications and was more directly applicable to various technologies, making it a safer, more understandable choice for recognition at the time. Additionally, the theoretical complexity and abstract nature of relativity made it less accessible and more contentious within the scientific community compared to the more concrete, experimentally validated photoelectric effect. As time progressed and further evidence supported relativity, its acceptance grew, but Einstein's Nobel acknowledgement remained for his work on the photoelectric effect, a testament to his broad and varied contributions to the field of physics. His other theories, while not Nobel recognized, continue to be celebrated and form the bedrock of modern physics, inspiring awe and wonder at the universe's mysteries.